Greetings all. Yes, thank you for attending. My name is TravisZalesky, and I'm here to talk to you today about habitat modeling using MaxEnt software. I will use a case study of chanterelle mushrooms as an example, but my goal is to focus on the methods and techniques that I used so that you are empowered to do your own MaxEnt habitat analysis on a species of interest to you. So first, a little background. Maximum entropy generally is a method of mathematical modeling with its origins as far back as the 1940s. It's an active area of mathematical and statistical research which seeks the, quote, probability distribution of maximum entropy subject to a set of constraints that represent our incomplete information, unquote. It has been widely adopted in many research fields. However, it has been particularly impactful in ecological niche modeling. MaxEnt software development recently has exploded, and dozens of peer-reviewed habitat models have been published using these methods, a few of which can be seen here. So one of the things that makes MaxEnt so powerful for species distribution modeling is its ability to enable presence-only prediction. Often, even in well-planned habitat surveys, species presence may be recorded with no reciprocal species absence data. In fact, it may be impossible to definitively prove species absence in a location, particularly for highly motile and far-ranging species. With MaxEnt, you don't need to worry about that. You don't even need highly structured habitat surveys using transects and quadrats or any of that stuff. This method is so flexible that you can use species presence data haphazardly collected from citizen scientists and uploaded to sites like iNaturalist. I obtained my species presence data from the Global Biodiversity Information Facility, GBIF, which compiles high-quality species presence data from many sources, including iNaturalist. And in my opinion, it is the best source of species presence data available on the web. However, to achieve high-quality results, some steps must be taken to reduce bias in this data. Firstly, as a supervised machine learning algorithm, MaxEnt modeling relies on a training data set and is validated using a testing data set. Many users, including some published authors, will rely on a random partitioning method, wherein a subset of testing data is randomly selected and removed from the overall data set. But due to Tobler's first law of geography, this violates the inherent assumption of sample independence, as testing points adjacent to training points will not be sufficiently independent to properly evaluate the model. This leads to inflated assessments of model fitness. Therefore, a better method of partitioning the testing data is to use a geographically structured method. Here, I've simply divided my study area into 5 rectangular bins containing an equal number of observations. Bin number 3 was randomly selected for testing and was subsequently removed from the training dataset. This maximizes the distance between testing and training samples, and it preserves the assumption of sample independence. So in this figure, the training data is the white circles and the testing data is the red triangles. The bins that I used are not actually labeled on this figure, but you can see here, this was bin number 3, and it was just randomly chosen, and all of this testing data was removed before training the model. The second potential pitfall that must be controlled for is the haphazard sampling method. Because the presence data lacks rigor, it is likely to be highly correlated with effort. In other words, species presence is more likely to be recorded in accessible areas near roads and trails, and is less likely to be recorded where human activities are low. This effort bias can easily be corrected through use of a bias file, which is simply an estimate of sampling effort. The simplest and most used type of bias file uses a target group sampling technique, wherein a large number of species presence data is collected for species similar to your species of interest. Once the target data has been assembled, a kernel density or other point density function is used to interpolate the data across the study area. Here, I used 260,000 wild forage mushroom presence records across 8 genus, which are, quote, likely to be targeted by the same collector or caught by the same collecting methods as a chanterelle. And generally, you can see high sampling effort in Washington, Oregon, and California, with lower sampling effort elsewhere. So, once you have your species presence data and your bias file ready, you can get your environmental data. This is the potential explanatory data for your habitat model, and it can be anything that you think might be ecologically relevant to your species. I chose to use the 19 bioclimatic variables published by WorldClim, as they are easily accessible, free to use, have a near global coverage, and are widely cited. But you can use whatever environmental data you have access to. Because mushrooms are non-motile, I also included elevation, slope, aspect, and soil pH for a total of 23 environmental variables. Another great thing about MaxEnt is that once you have an established model, it is simple to make forecasts based on environmental changes, such as under climate change. By simply changing one or more of the explanatory variables and passing them to the projection layers, you will get a forecast of how the habitat is projected to change in response to the changed environment. And we will see an example of that here shortly. Okay, so once you've collected all of your data and you've run your model, you must then validate your model. Evaluation is a critical step in any classification model, and there are several methods for evaluating MaxEnt models. The first two methods are threshold dependent, meaning that the fitness score is a function of some arbitrary threshold value. There's the omission rate, shown here in blue, which is the fraction of training or testing points which are not captured at a given threshold. And there is the proportional predicted area, shown here in red, which is the fraction of the study area above a given threshold divided by the total study area. High omission rates and low proportional predicted area are necessary for a well-trained model, but they are not sufficient to prove model fitness. So briefly here, on the x-axis of this graph, this is the actual threshold value. And in blue, we have the omission rates for the testing and training data, which should closely match with this black line, the predicted omission rate. And in red, this is the proportional predicted area. It should have this kind of downward sloping curve. My slope here is very steep initially, and this is because I had a very large study area that had a lot of unsuitable habitat. So your curve might be a little shallower and more gradual than what you see here, but it should have this kind of shape. So the number one test for maxent model fitness is the receiver operating characteristic, area under the curve. The ROC is a complicated statistical test of model fitness, but basically it's just a probability function that instances are correctly classified by the model. The area under the ROC curve will be 0.5 for a completely random model, and the approximate upper limit is 0.98, roughly. The higher the AUC, the better the model is. But be careful to use your bias file and geographically partition your testing data, or your AUC will be artificially inflated. Importantly, all of this is calculated for you by the software. All you need to do is compare models and try to maximize your AUC. So here, these two lines, these are the actual ROC curve, and the AUC is reported here, and it's approaching the theoretical maximum. So this would be considered a very good model. Another way that you can evaluate your model is to evaluate the explanatory variables themselves using jackknife testing. Jackknife testing iteratively performs many models using only a single variable and also systematically eliminating a single variable. Then, by comparing all of these models, you can get an idea of which variables are most important and which might be superfluous. In my example, precipitation of the coldest quarter was identified as the most important single variable, while some other variables like slope and aspect were not particularly informative by themselves. So after all of that setup and model optimization, you've run your model and you've gotten your results. The default maxent output is a continuous species probability value, but I have simply reclassified those results into 5 discrete classes of habitat suitability for visual clarity. And you can see here that my projected habitat for chanterelle mushrooms is extending from Central California along the West Coast all the way up to Southern Alaska. And here you can see that the projected habitat is matching very well with the testing data. So overall, this is a really good model. And here we have the difference between the current conditions and 3 climate change scenarios utilizing the projection layers option that I mentioned earlier. The details of these climate change scenarios are not really important, but from left to right, they are a low, medium, and high emissions scenario for the year 2100. And you can see that the models generally agree with each other, with improving habitat in the north and degrading habitat in the south, and that the degree of change becomes more dramatic as the projected emissions increases. Okay, so how do you do this for yourself? I said at the beginning that I wanted to empower you. So here are 3 options for you to get started. For those that have access to and are familiar with ArcGIS Pro, there is a presence-only prediction tool in the Spatial Statistics Toolbox, which utilizes maxent methods. For intermediate users looking for a free and open source option, there is a purpose-built Java application, which is available for download from the American Museum of Natural History. And this is what I used for my analysis. And for power users, there are various packages available for your preferred programming language. If you would like to learn more about where to find or how to use any of these tools, You can feel free to reach out to me after the presentation, and I would be happy to get you more information. Thank you all for listening. I hope that this presentation has given you the necessary tools and background to be able to perform and evaluate MaxEnt models for yourself. I'm eager to take any questions you may have, and I've provided a few suggestions here for discussion. Are there any questions?